Hi, good morning, everybody. Well, it's morning right now, but maybe it won't be morning when you watch this. Hope you're all doing all right and everyone's safe at home, and it's gonna be okay. Like I said in my email, it's not the optimum moment, but it's not the worst time because we're really close to being done with what we need to learn. We pretty much finished Unit 8 before we left. All we were going to do this week was we were going to do a lab and then we were going to test. And then the next 2 weeks is learning Unit 9. And so we really only just have one more unit, and it's a really short unit to learn. And so stay with me. Don't give up on this because the AP test is coming, and I know that you guys are all very capable of passing that test. So yeah, so kind of today what we're going to do is we just had a few things from the last notes that we didn't quite get to because we spent the whole day talking about titrations, which was great. So we're just going to briefly cover those notes, and then I'll kind of do a review of what Unit 8 is about. And then as well, to help you prepare for the tests that we'll take on this unit, I'm going to make a practice test. It will either be on Canvas or AP Classrooms. The website will say once I get it figured out. But that practice test for the multiple choice will be very similar to the actual test. Once again, not word for word, but topic for topic. So if you take the time to understand those practice questions, you should be able to do very well on the actual test. And then for the FRQ portion, last time in class you got some FRQ practice questions. I'll post the answer to these as well. And so these are kind of the way you can help prepare yourself for the FRQ portion of the test. And I'll post the answers to this. If you weren't there in class and didn't get this last Friday, I'll post a link for you to print this off as well. Okay, throughout this whole adventure together, please, please, please don't be afraid to reach out. Okay, message me through the Remind, or send me an email, or through Canvas if you're feeling stressed or overwhelmed, or there's something I can help you with. Okay, because I'm still here for you guys. We're just not in the same place anymore. Okay, and I'll let you guys know I'm working on some ways in which we can do some virtual conferences or classes together, so we can still have that interaction. Okay, all right, let's go ahead and cover this, and then we'll get to the review. Okay, so last time we left off on learning about titrations, and we drew pictures at the molecular level of what's happening along each step. Talked about how the equivalence point is when the moles are equal, and so you can find the unknown that way, so on and so forth. For an acid that is polyprotic, meaning it has more than one hydrogen, so for example, this graph is for phosphoric acid, which is H3PO4. So when you have a polyprotic acid, more than one hydrogen, when you do a titration of it, if you continue to go, you'll actually get multiple equivalence points for every hydrogen that it's dropping. So as you can see here, this right here is when H3PO4. This is for H2PO3, HPO3, and then once again, you could have another one because this is a triprotic acid. Same thing, and one of you asked a really good question about this in terms of the determining the Ka value. Right, we talked about that, the halfway to the equivalence point. So in this case, the equivalence point is 50, so halfway would be 25. Right, so if I mark that and take it over here, that tells me the pKa of the acid. Now when an acid is polyprotic, having multiple hydrogens, you actually have multiple Ka values. So this would in a sense be pKa1 corresponding the first loss proton. And then same thing here. Let's see, because that's between 150, so 75. Right, so this would be our pKa2 value, so on and so forth. So that's kind of how a polyprotic one will look like. You just have different amounts, but the idea of the titration is still the same. All right, the last thing we were going to cover is kind of talking about the structure of acids and how the structure of an acid can help you understand its strength. Now, once again, you need to know the 7 strong ones memorized, but this is kind of a way when you're looking at weak acids, you can identify which one is stronger of the weak, and it also kind of helps us understand what makes the strong acid strong. Because we talked about how the definition of an acid is a substance that donates a proton. So the better it is at donating its proton, the stronger the acid will be. And so its structure, if its structure is in such a way that when it gives up the proton, it's still stable, then it's a pretty strong acid. So the first thing, one of the trends or patterns we can look for is strong acids have very weak conjugate bases, meaning because a base typically accepts, but if it's really strong, right, so like hydrochloric, that's why it's only a one-way reaction, is because Cl- is such a bad base, it never grabs back onto that hydrogen and goes the other direction. So the weaker the base, or the weaker the conjugate, the stronger the acid. So the weaker, oh, that's a little squished. The weaker the conjugate, the stronger the acid, or vice versa. So one of the things that will make a conjugate weak is based off its electronegativity. So acid strength, what this says right here on the line, it says acid strength decreases with a decrease in electronegativity. So the higher the electronegativity of what the H is bonded to, the stronger the acid will be, because a higher electronegative atom can stabilize itself better. Okay, so for example, if we wanted to arrange these acids by strength, we can see, so what we're looking for here is electronegativity trends. So really all we're focused on is just CLI and Br, because the other two pieces are the same, and it's never about the H, because the H is what's being donated. So if we go to our periodic table, once again the trend says that acid strength decreases with decrease in electronegativity. So since Cl has the highest electronegativity, HClO would be the strongest acid, because this one has the highest electronegativity. And then from there it would go, so this one's going to be bigger than HBRO, and this one would be bigger than HIO. Like so. The other thing we're going to look for when you're looking at the structure of a substance is the number of oxygens that an acid has attached to the central atom increases the strength of the acid. Once again, because it's all about how it stabilizes the structure. So for example, we see here in this picture, once again, so we have some Ka values. Remember that the bigger the Ka value, the stronger the acid. And so notice that this is our strongest acid, and it has 4 oxygens around it, 3 oxygens, 2, and then just 1. Notice once again, it's all Cl, so we're not taking into account the electronegativity trend, but just the number of H's, or number of oxygens that it has around it. Okay, the last page of your notes, we're going to hold off on for now. It deals with pH and solubility, and we're going to do for our lab an activity that really would help us understand that. So we're going to put it on hold, and when we get back together, when we do that lab, we'll also learn that topic. So there won't be anything on the test about 7.13, so you don't need to worry about that.